Anyone else?
My name on it.
Okay.
You have a pen and paper?
I do not.
Okay. I'm gonna go get
All
my
right.
pen.
All right, thank you, sir. Okay, let's talk. Everyone's turned in, right? All right, let's talk about this. So you could get yourself into some big trouble here if you look at this and say, okay, I've got quadratic and linear, and then you start trying to do this thing where you try and match it, where you sit here and go like this. And then you say, okay, I need to try and force the top to look like this. If you do that, you're going to be in big trouble. Because you only do this when?
Irreducible?
When this is irreducible. This is not irreducible, that's factorable. So that, I don't know, maybe you could get to it that way still. But that would probably have taken you quite some time. Instead, what you do is you factor the denominator to be what? X minus 2, x minus 3. And you don't need long division here because the power up top was lower than the power down here. So now you have to do your partial fractions. You've got to make x minus 4 over x minus 2 times x minus 3 look like, what, two distinct linear factors? So a over x minus 2 plus b over x minus 3. And then you play your little game here and you should get this. And then let's see, if you want to kill this one off, you let x be what? 2, right? 2, and if I let x be 2 here, we get negative 2. If I let x be 2 here, negative 1, so negative a. That means a is 2. And then if I want to kill off this one, I let x be 3. So I put a 3 here, I get negative 1 equals, that one's gone. Put a 3 here, I just get b. So b is negative 1. So this integral becomes, what, a over this, so 2 over x minus 2, ooh, that's a minus 2, plus b, which is negative 1 over x minus 3 dx. Yeah, and then those you can do just one by one, right? So the first one, you pull the 2 out, and it's natural log x minus 2. And then the other one, you pull the negative 1 out, and you get natural log x minus 3 plus c. That's it.
Question.
Yes?
Can you move the negative to the front of 2?
Well, no. And not unless you make that a negative also. Like, you would have to put a negative, and then positive. The 2's not negative, right? So if you put a negative out there, it would change it to negative. So I would have to look at exactly the way you have it written, if you have parentheses or not. But right, this negative is only on this piece, not on this piece. So you can't say that that's negative also.
So when it has a negative out front, did you say the book will sometimes raise it to a power?
Yeah, sometimes the book will take that negative and put it up here as a negative 1, and then write that as 1 over that. In this case, I doubt they would, because 1 over this isn't any nicer, like, you know what I'm saying? So they just probably would leave it like that. Okay, that's the way it should have been done, the most efficient way, the fastest way. All right, let's pick up where we left off last class. We were talking about the fundamental theorem of calculus, and specifically that there is a connection now between a derivative and the antiderivative, and geometrically that it gave us some idea of this area concept, right? Area below a curve. And I wrote the fundamental theorem of calculus up here. It's not on screen, but it's in the notes, but I'll be referring to this throughout class. So if you have a curve, right, and you want to find the area underneath this curve, all you need to be able to do is find the antiderivative. if you can find the antiderivative, and you know the two endpoints, A and B, then once you find the antiderivative, you'll plug the number B into that antiderivative. That'll give you a numerical answer. Then you plug the A into that antiderivative. That'll give you another numerical answer. You subtract the two. That gives you what we refer to as the net area. And I ended class showing you an example with cosine that we integrated over 2 pi, and we got a net area of 0. Remember that? And that was because some of the bottom area canceled off the top area. So that's why we say net area. All right? Now, there are two versions of the fundamental theorem of calculus. There's version 1 and version 2. And I'm opting, although some instructors would be very upset with me for doing so, I'm opting to not focus a lot of attention on the first version of the fundamental theorem of calculus because this is the one at the end of the day that's used all the time. But if you want to read for yourself, it's in the book. They show you the first version. We're going to put that behind us, okay? We're just not even going to look at it. All right, so this is why we spend so much time finding antiderivatives, is because we need them to be able to do this. So I wanted to start class with this example. Find this.
So this is still part of chapter R?
Yes, this is still chapter R. It's a combination of 5.2, 5.3, and 5.5, I believe. Now, when we were doing integration before, we didn't have these numbers, right? And when you don't have those numbers, it's called an indefinite integral. When you have numbers, then it's called the definite integral. And I did refer to that last class. Do you understand why we would call it the definite integral? Because we should get some numerical answer, as opposed to when these numbers weren't there, our answer had a plus c in it, right? Which meant that there was a whole family of functions, infinitely many functions that could qualify to be an antiderivative. But as soon as you put the numbers there, it becomes something completely different. It's a numerical value, and so it's definite. Make sense? All right. So to do this problem, all we need to be able to do is find the antiderivative of this thing, of little f, right? So that whole thing is little f. We need to find the antiderivative of it, which we will say is capital F. So I'm going to put equals here. What is capital F? So we're going to write down capital F, then we're going to write this bar here and the two numbers like this. So what is the antiderivative of 5x? Because we can split these up because they're subtraction, right? So 5 halves x squared minus, now what's the antiderivative of 5 raised to the x? You got to be a little careful here. So this is in your formulas. If you, someone tell me what formula this is. It's one of your basic formulas. Formula number 5. Formula number 5. Everyone see formula number 5? Formula number 5 says if you find the antiderivative of a to the u du, the antiderivative is a to the u over natural log a, right? Plus a constant. So a, you know that you're using this formula because a is a number. The variable in the problem is u. So here a is 5, right? And the variable we have is x. So that's why we're using this formula. Now, does this formula work if you have e to the x?
No.
Well, you would have this, and then you have natural log of what? E, but natural log of e is 1. So this formula actually works for all exponential functions. In the special case that the base is e, then this formula just turns out to be e to the x, right? So this is a more general formula that you can use for all exponential functions. All right, so what is this going to be? 5 to the x over natural log 5, right? And then I'm going to put a bar here. and I'm going to put 0 on the bottom, 1 on top, like that. Then, as you're going to see me do throughout the rest of today, I always give myself 2 sets of parentheses. I put a subtraction sign between them, and that's for these 2 pieces right here. So we want here capital F of 1, and over here we want capital F of 0. Now this is capital F, right? Our antiderivative is capital F. So we're just going to plug 1 into this, then we're going to plug 0 into this, subtract the 2, we got our answer. So let's plug in 1. What do we get when we plug 1 in right here? Just 5 halves minus what? 5 to the first power, which is just 5 over natural log 5. And then we plug 0 in. What do we get when we plug in 0? 0 squared, it's gone, right? Minus, what's 5 to the 0? 1. 1 over natural log 5. So we'll try and clean this up a little bit. This is 5 halves minus 5 over natural log 5. And then what about this over here? Plus, right? Because minus a negative, so plus 1 over natural log 5. See, there's no more plus c's anymore, right? No more plus c's. Anything else we can do? We can put these 2 together. They have the same denominator, don't they? So this would turn out to be 5 halves minus 4 over natural log 5. Questions? You can leave it like this, yes. Now, that's what we call the exact answer, right? That's the exact value of the area, the net area. But you could approximate it by getting your calculator out and getting a decimal for this. So with this, I have a picture of, this is the actual picture of this function, this blue curve between 0 and 1. And so you can see we have some area that's below the x-axis. We have some area that was above the x-axis. When you put those 2 areas together, the net area is this number. Is that positive or negative? You'd have to get a calculator out, wouldn't you? Like this is what, 2.5? You'd have to get your calculator out and see what this is to see. Because maybe, does it look like there's more positive area or negative in that picture?
It's positive.
It looks more positive? Is it barely? Barely. So what did you get for this whole thing? Did you?
0.015.
0.015. So really close to being the same area, right? Not quite though. All right, let's continue. We did this one last class, right? How about this one? X cosine x. Integral 0 to 2 pi. So Ron, I don't want to bore you today. So maybe you can help us, Ron. Any ideas on antiderivative for that? On how to get the antiderivative for that? Integration by parts, good. So we're going to create a little table here. Now, here's the thing. This is a definite integral, right? We need the antiderivative. So I recommend that if you're going to do your antiderivative, you do that separately over here. And you set up an indefinite integral like this. And you do everything that we spent the last few weeks doing. And you find the antiderivative. And then you take that and you bring it back over here and you plug it in here, and that's your capital F. All right? So this part right here might take you some time to do. Understand? So integration by parts, Ron. X, okay. And then cosine x dx here. Okay, so Ron was able to identify that that's integration by parts. that by choosing u to be x in the new integral, that'll be gone, right? And then we have to be able to integrate this, which we can. So du is dx, v is what? Sine x. And so this part, I'm not working with this yet, right? I'm still over here. This integral becomes equal to ultraviolet x sine x minus integral of voodoo, v du, right? Which is sine x dx. And now you have to be able to integrate sine. What's the antiderivative of sine? Negative cosine. But there's a negative out here already. So the double negatives are going to give me a positive, right? And what have we always been putting out here? Plus c. Well, here's the deal with the plus c. In a definite integral, the plus c is not going to matter. Because think about it. In this part right here, f of b minus f of a, isn't this one going to have a plus c in it? This part right here would have a plus c. And wouldn't this one have plus c also? And so you're going to wind up taking the c that's on this one, you're going to subtract the c on this one, they're going to go away. So the c's are not relevant to us with definite integrals. We good? All right. So I'm going to come here now, I'm going to continue this problem. This is equal to, I'm writing this step right here, capital F of x. So x sine x plus cosine x, 0 to 2 pi. And then I get to plug in two numbers. So I'm going to have equals, two parentheses, separated by subtraction. And just always remember that the b goes first, right? B goes in first, then the a. If you get them backwards, you're going to be off. The answer is going to be actually opposite in sign. So if the answer is supposed to be 2 and you do it backwards, it's going to be negative 2. So the good news is that you'll still get the correct quantity. It'd just be off by a sign. But it'd be wrong. Right? Okay. All right, so let's plug in 2 pi for x. So we get what? 2 pi times sine of 2 pi plus cosine of 2 pi. And then over here we plug in 0. We get 0 times sine of 0 plus cosine of 0. What is this? Let's see. What's sine of 2 pi? 0. So that whole first term here is gone. Right? This whole thing is gone. What's cosine of 2 pi? 1. So this equals 1 minus parentheses. This is 0. Cosine of 0 is 1, which is 0. So this one, again, it turned out, and it's just a coincidence, okay? It's not a coincidence, but it's not always going to work this way. You're not always getting 0. But look, the function is different. This was the problem I did last class where we had cosine x, and I think I could convince everyone from symmetry that the part above was equal to the part below and they cancel each other out. This function, x cosine x, is not symmetric, but it does turn out in this particular case that the area above the x-axis is equal to the area below, and they also cancel each other out. So the net area was 0. Questions? No? Okay, so we're going to get into some properties now of definite integrals. I'm going to make this a little larger so you can see this. So I'm in R23 here, note R23. Let's look at the first one. The first property says that the integral from a to a of f of x dx is 0. Does that make sense to you? If you integrate from a to a, that's always 0? Yeah, because you have a function, right? And here's a, and you're looking, here's the function, and you're trying to find the area below it, but only at one point. And so if you look at a point and you go straight up, you draw a line, and the line has no area, right? So it would have 0 area. So that makes sense? Okay. The next property says that if you integrate and you go from a to b, that's equivalent to going from what? B to A and change the sign. But you have to change the sign. So in other words, if you have an area under a curve from A to B, like this, whatever that area is, here's the integral that represents that. If you switch the order and you go B to A instead, then what happens is, remember the differential here was the width of the rectangle? You remember that? I was going to give you a quiz that was going to ask you those two things. What does this represent? What does this represent in the picture? You remember what this represents? Remember, if you take a little slice, a little rectangle out of this, we're going to have an infinite number of them in here, right? This integral sign meant we're going to add up an infinite number of them. The f of x represented the height of the rectangle. The dx represented the width, right? So when we get this dx in this formula, it's how wide this is. But if we reverse the order of b and a, that width becomes negative. It's a negative number instead of a positive number. So what happens is that when you have a negative number here, this will be a negative number, it's going to change, all it's going to do is have the effect of changing the sign of everything. So in order for these two to be equivalent, you have to put a negative out here. So that's what that property says. You switch the order of integration, and you're going to pop a negative out or change the sign of the answer. The next one, the integral from a to b of a constant. K is equal to K times b minus a. Does that make sense why that would be? Let's draw it. That's a constant function, right? Constant. So maybe it just does this. It's k units high, right? That's how tall it is. And I want to know the area between A and B. Well, how wide is it? How wide is this thing? It's b minus a, right? That's how wide it is? How tall is it? K, so k times b minus a. Now, we're not going to integrate constant functions very often, but just FYI, all right? So you realize where that comes from. All right, the next one, we saw this next property for when we were doing indefinite integrals. If we ever had a constant, we could always just pop the constant out. Why am I using k and not c? We use c for the constant of integration, so this is just a different constant. So when we have constants, they just pop out, right? That's all that property says. How about this one, property 5? If f of x is greater than or equal to 0, then the integral is what? Greater than or equal to 0. So it says if you have a function on some interval a, b, and you promise me that that function is above the x-axis, right? Function being positive, a function being greater than or equal to 0 means that it's above or equal to the x-axis, right? Then that means if you're looking for the area, that area is going to be positive, isn't it? If the function dips below the x-axis, then you can't guarantee that, right? It might cancel out and become negative. So that's what the next property says. 6 says if your function's always below the x-axis, then your answer is going to be a negative answer. Any questions on these properties? I'm moving through them kind of quick, but are there any questions on them? Does it all make sense, like logically make sense to you? All right. Property 7 says that if you are looking at a function and you're trying to find the area between a and b, then you're allowed to find a number in between a and b, let's call it c, and you can do two areas. You can do this area, and you can do this area, find them separately, and add the two answers together. That would make sense to you? That you could do that? The total area? Yeah, y'all are just like, yes? The total area is this area plus this area. This area is the integral that goes from a to c. This is the one that goes from c to b. So that's what that's saying right here. The integral from a to b is equal to the integral from a to c first, then the integral from c to b. Understand? Add those two areas together. As long as the c's between these. Of course, if c's out here, that doesn't work. So that's what that first condition says. C must be between the two. All right, the next one is a nice result. Okay. If f is even, then the integral from negative a to a of f of x dx equals 2 times the integral from 0 to a of f of x dx. What does it mean for a function to be even? So you have to remember what this means from, well, you probably saw that in college algebra, and you probably saw it in pre-calculus, and probably in calculus 1. What does it mean for a function to be even? You remember? Cosine is an even function.
Oh, when you fold it.
Yeah?
They're like,
Yeah. They're like mirror images of each other. Okay, so look at the picture I have here. Do you agree that if I take what's to the right of the y-axis and I reflect it over the y-axis, I get exactly what's on the left side? So it's a mirror image over the y-axis. That's what an even function looks like. Now, technically speaking, this is really what an even function, the property of what even functions do. Even functions, if you plug a number into them, you get the same answer as when you plug that same number in negative. That's what it means for a function to be even. I'll give you a very simple example of an even function, x squared. If I plug 2 into that, don't I get the same thing as if I plug in negative 2? If I plug in 3, it's the same as negative 3? That's an even function. And if I graph that, it's a parabola, and it looks like a reflection over the y-axis. So what this is saying is that if you integrate, not from a to b, do you all see that? From negative a to positive a, then that means you're picking up both sides of the y-axis. You're going out to a, right? But from negative a. So you see you've got like the left side and right side. If the function is even, then whatever it does over here, it's got to be a mirror image of it over here, something like that, right? So if I'm trying to find that entire area, do I really have to find the whole thing? No, all I have to do is what? Go, that's right, double the area on one side, and that's what this is. 0 to a would be from here to here. Take that answer and double it. That only works if it's an even function, though, right? Only if it's even. What if it's an odd function? Well, odd functions don't behave like this.
are these going to cancel?
That's right. That's exactly what will happen. An odd function, whatever this does over here, it's got to do not the same thing on the other side. It's a double reflection. It reflects over the y-axis first, like this, and then it reflects over the x-axis, like this. And so this is the picture. The black there is the odd function. The green was just to show you it's a reflect and then a reflect. So whatever this area is, right? This area is exactly the same, but negative. So when you put the two together, you get 0. Only if it's an odd function. How can you check to see if a function is odd? Like I showed you even was this, right? What is it for odd? It's negative f of x is f of negative x. That's what it means for a function to be odd. Can somebody give me an example of an odd function? Sine is an odd function. Not quite as easy to check, though. Right? How about this? X cubed. Does it make sense that that would be an odd function? What's the power on it? It's odd, right? So let's see what happens if I plug a negative number into this. I plug in -2, what do I get? -8, right? What if I plug in +2? What do I get? 8. They aren't the same, right? They aren't the same? What I get when I plug in a negative number, -2, is not the same as plugging in 2, is it? It's the opposite of what I get when I plug in 2. So if I were to change this to a negative, this would be negative, and then they would match. I hope you see that. This right here is what this is saying. Okay, those are the properties that we have for definite integrals. And now we're going to, let's do a couple of examples. I'll give you something a little more complicated. Integral -π/4 to π/4 of tangent x over 4 plus x squared dx. Anybody have any ideas here? Just looking at this, just what's your first impression? You're thinking, you said trig substitution in what sense? Like,
Because the bottom is a squared plus a squared.
so you're seeing like an a squared plus x squared? So thinking maybe trig sub. Okay, that's one train of thought. Any other trains of thought?
Isn't that like the tangent inverse in the bottom?
The bottom is the derivative of arctan, isn't it? Like if you look at the bottom, it's really this, isn't it? And that is the derivative of arctangent of something, right? There's a little more involved there, but we've kind of come to understand that when we see this, we're thinking arctan in some way, right? Okay, so trig sub, arctan. What's that called? Integration by parts. Okay, so if we do integration by parts, you have to choose a u and then you have to choose a dv, right? So sounds to me like almost every technique that we've covered is what you're talking about. So that seems like trouble to me if everyone's seeing a different technique here. Can I point something out, though, just also what I want you to be thinking about? We're going from negative a to a also, right? And we do know that there are some properties that we can use when we have negative a to a. If it's an even function, then I can just double the answer, right? I go from 0, like I could go from, instead of negative π/4 to π/4, I could go from what? 0 to π/4 and double that answer if it's an even function. Is that an even function? I don't know. Is it odd? If it was odd, what would the answer be? 0? Right? All right. But let's get back to trying to integrate this, and then we'll talk about that even odd thing again. I think everyone is kind of seeing kind of bits and pieces of the right thing. You know, you're seeing the arctan in there. You're seeing trig sub. The problem with the trig sub was that we would first have to rewrite this, right, as like square root of 4 plus x squared. and then squared to be clever and put it under a root, then our trig sub that we would use here would be x would be what? You remember what it would be? It'd be 2 tangent theta, right? X would be 2 tangent theta, which means this would turn into tangent of 2 tangent theta, and that's we haven't even seen anything like that before, right? That could be major trouble. And then what was the other one? Integration by parts. What would you choose for u? What would you choose for dv? If you choose that for u, what's the derivative? Secant squared. And then this would have to be your dv, which is 1 over that, which when you integrate would be what? Arctan? I may as well write this down. U would be tan x, right? dv would be 1 over 4 plus x squared dx. The derivative down would be what? Secant squared x dx, and v would be 1/2 arctan of x over 2, wouldn't it? Because a is 2. And then look at voodoo. No thank you. Right? No thank you. We've never seen an integral with tangent inverse mixed with secant. We've seen tangents and secants together, right? But not arctan and secant. So what should be happening in your brain is you should start to concede to this integral. You should start to understand that, look, I don't think I'm going to be able to integrate that. Yes?
Can we have it sine everything times cosine everything? Can we do that? Oh, no.
No, because there's not addition.
Yeah.
We couldn't switch around the x squared plus 4 because it'd have to be 1 over x squared plus 4 for your u.
It would have to be 1 over x squared plus 4. And then the derivative of that would be, if that's your u, the derivative would be a quotient rule. It'd be a mess. So are we all kind of seeing that this is an integral we can't handle? We can't. It's not going to be easy to do it. So that means that if we can't integrate that easily, this is the thing that should be making us think that maybe there's something easier we can do. If it was even, right? If it was even, right? If this is an even function, then I can go from 0 to power over 4, right? And double that answer. But I still have to integrate it, don't I? And I don't know how to integrate it. So my only hope is that this is an odd function. Because if this is an odd function, what's the answer? 0, I don't have to do any work, do I? I don't have to integrate a single thing. So what I'm going to hope for right now is that that's an odd function. And I wrote down what it meant to be odd, right? An odd function. Not just what it means to be odd, Kiki. Are we not joking around anymore, Kiki?
Do you want a retort? I can come.
No, you don't have to. All right. Odd function check here. This is the integrand, right? That's what I'm looking at as little f of x. Is little f of x odd? So let's just write down this function. Tangent x over 4 plus x squared. And I'll remind you of what it means to be odd. Odd function. To be odd means that when you plug in negative, it's the same as the function without negative, right? Change the sign. This is the definition of an odd function right here. So if that's the function, let me check this first. What would this be? Let's see. F of negative x would be tangent of negative x over 4 plus negative x squared, right? Yeah? What happens if I take negative x and square it? It's still x squared, right? Still positive x squared. So this is just tangent negative x over 4 plus x squared. And now what we're going to need to know is what happens if you have a negative inside of a tangent? You can pull this out front because tangent is an odd function. Now, does your formula sheet say that? I wonder if they even give you that. You need to know that, but yes. In reference page 2, fundamental identities from pre-cal is that tangent, see it, tangent of negative theta equals negative tangent theta? Y'all see that? So I know that I could rewrite this as what? Negative tangent x, right, over 4 plus x squared. That's what I get when I plug a negative into this function, right? Now let me check to see what this is. So what do I get if I put a negative in front of the function? So here's the function, right? Put a negative in front of it. So negative f of x will be a negative in front of tangent x over 4 plus x squared. It's the same thing, isn't it? That negative right there can be up top or can be out front, right? And that negative right here, I can just pop it up here. And so what we're saying is that f of negative x, right, is exactly equal to negative f of x, which means it is an odd function, which means the answer is 0, with no work at all. All right? That's using that property. Do you understand? That could be a disaster on a test. You're trying to integrate that, right? For like 30 minutes, you're trying to integrate that when the whole time it was using this property of an even and odd function thing. Right. So the answer is 0. So I'm going to conclude that. I'm going to say since the integrand is an odd function, the integral from negative pi over 4 to pi over 4 of tangent x over 4 plus x squared dx equals 0. Now what if this had gone from, in the original problem, had gone from negative pi over 4 to pi? We'd be SOL, yes. We would not be able to do that. I picked a good problem. That was a good illustration of those properties.
Is there a way to do that?
There is a way to do that, but you would do it with power series. You would do a power series expansion of that, which we will do in Chapter 8. So there's a way around things that we can't integrate easily. Let's do another one. This will be our last one before we start the next section. Integral 0 to pi over 6 of t sine 2t dt. So when you're looking at this, you should be thinking, first, can you integrate it, right? Can you actually integrate this? Yes? This does not have that form of negative a to a, right? So there's no way we could ever use that property anyway, if it was even or odd, right? Nothing could happen because this doesn't have that format. So the integration on that, what do you got for the integration on that? By parts? By parts? So I'm going to set it up over here. U will be what? T. dv will be sine t, or sine 2t dt. All right. du dt and v. Negative 1/2 cosine 2t. So this integral right here, after ultraviolet minus voodoo, becomes this times this. Ultraviolet. So I put the negative 1/2 in front of the t, and then I wrote the cosine 2t. Minus voodoo, so what should I write next? Plus 1/2. Integral cosine 2t dt. And we can integrate this, right? Cosine, antiderivative cosine 2t is 1/2 sine 2t. The 1/2 is going to hit this, become a 1/4. So we're there. Negative 1/2 t cosine 2t plus 1/4 sine 2t plus a c, but I'm not going to need the c, am I? Are there any questions? All right, so we've got, what does this mean? It means we're going to write down the antiderivative, right? And then put that little bar there in the two numbers. So I've got negative 1/2 t cosine 2t plus 1/4 sine 2t, 0 pi over 6. May I erase this side? Anyone need this still? We're all good? Equals two sets of parentheses. Let's plug in pi over 6. All right. Negative 1/2 times pi over 6, negative 1/2 times pi over 6, cosine of 2 times pi over 6, and I'm not going to have enough room, plus 1/4 sine of 2 times pi over 6. That's what I get when I plug in pi over 6. Minus what I get when I plug in 0. I think this 0 is a little easier to plug in, right? What do I get when I plug in 0 here? 0. It's all gone, right? Because that 0 right there? That's all gone. So I've got 0 plus 1/4 sine of 2 times 0, which this is going to be 0 also, but this one was a little more obvious. Are we good or not? Any questions on where any of that came from? Is everyone happy with the fact that this is 0? Sine of 0, 0, gone. Okay. Now, this is the only piece that's left, right? But I've got to clean this up. This looks terrible. So equals, how about these two together give me negative pi over 12 times, what is cosine of, isn't 2 pi over 6 the same as pi over 3? What's cosine of pi over 3? Did you say 2 over 2? Root 3 over 2. Or is it 1/2? Hold on. Where's pi over 3?
60 degrees.
Right there. Cosine is which one of those points? The first one, which in this case is 1/2. So this right here, everyone okay? 2 pi over 6 is pi over 3. Right? Pi over 3. Cosine of pi over 3 is 1/2. So this becomes times 1/2. Plus 1/4 times, now this is sine of pi over 3. Sine of pi over 3 is the y coordinate, which is the root 3 over 2. So root 3 over 2 here. And that's it. I'll clean it up a little bit more, but I think we're there. Get negative pi over 24, and then plus root 3 over 8. Could I combine those and get a common denominator? I could. I can multiply the top and bottom of this fraction by what? 3. Negative pi plus 3 root 3 over 24. That might be what the book has. Or they might put 3 root 3 minus pi over 24. Either way, are we all right with this? So if you back up and look at things, really the only difference between what we're doing now and what we did before is that once we actually get the antiderivative, we've got to be able to plug two numbers into it. And once we plug those numbers in, we subtract. That's it. But it's calling back, it's requiring that we can go back and recall things like what's cosine of pi over 3, and later on we'll have other things that, natural log of this and what's that equal to, and so we might have to go back and pull things out of our short-term memory cracks and find stuff that we've filed away a long time ago. We're going to do, I said we're going to do one more and move on, but I'd like to take the problem we did for the quiz. The problem we did for the quiz was integral x minus 4 over x squared, what was it, minus 5x plus 6? That was the quiz problem, right? And I'd like to just add one thing to it. I'd like to make it a definite integral. Does anyone remember what the answer was? It was 2 natural log x minus 2 minus x minus 3. That was our antiderivative, right? That was the correct answer to the quiz. And now we have the bar and the 0, 1. I think what you're going to see right here is how important the absolute value around, when you do the antiderivative, how important that absolute value is. So let's go back and just take a quick look back at the natural log function, because we're going to need it now, we're going to need it later. If I were to graph natural log, it looks like this. In fact, it hits right here at 1, at 0. This is the natural log of x. It has a vertical asymptote at 0, right? The graph does not exist over here. So when you talk about the domain of the natural log function, the domain is everything 0 to infinity, right? Not including 0. You cannot plug 0 into the natural log function. It's undefined. You can't plug negatives in. So these absolute values are going to save us when we try and plug 1 in here, right? It would be 1 minus 2, which is negative 1. And if we didn't have the absolute value there, we can't even do it, right? Some other things before we get back to this, some other things about the natural log. What is the limit as x goes to infinity of the natural log of x? Infinity. So why is that true? What this limit means is as you're walking along this function, right? And your x values are going out to infinity, what are your y values going to? They're going up, right? They keep going up and up and up. It's kind of a slow growth, but it does go up, right? Forever. And so as x goes to infinity, the graph goes to infinity. Yes? What about this? What's the limit as x approaches 0 of the natural log of x from the right side of 0? Do you remember that from Cal 1? So this means instead of walking out this way forever, start to walk towards what? An x value of 0, right? And where does the natural log function go? It goes to negative infinity, doesn't it? So this limit is negative infinity. As you approach 0 from the right, the natural log function dives down to negative infinity. As you approach infinity, the natural log function grows without bound. Okay, back to this. Sorry. So we're going to have two sets of parentheses here. Subtraction sign between them. First plugging in 1, I get 2 natural log of 1 minus 2 minus natural log of 1 minus 3. And then plug in 0, 2 natural log of 0 minus 2 minus natural log of 0 minus 3. I'm not saying absolute value, but it's in there, right? Okay, what is this going to give me here? Negative 1, absolute value. 1, natural log of 1. I just drew it, right? Remember? Natural log of 1 was 0. So this whole thing here becomes 0. Times 2 is still 0. So I got 0 minus, what's this? Natural log of 2, right? Minus, over here, this is what? 2 again, right? So 2 natural log 2. And then right here, minus natural log 3. Let's clean this answer up. This is negative natural log 2, and then distribute through minus 2 natural log 2, and then plus natural log 3. Can I do any more cleaning up here? These two can come together to give me how many of them? Negative 3 natural logs of 2 plus natural log of 3. Can I do anything else? We can combine the natural logs. Let me try this, see if you go for this. Do you agree with that? Just change the order. Right? Yes? Do you agree with this? Where'd that come from? The 3 came up as a power on the 2. 2 cubed is 8. What do I do there? If you have 2 logs, right, being subtracted, you can turn it into a single log with division. So you might want to go review properties of logs. This seems kind of like, what? I'm using this property right here. My guess is that's probably on your sheet somewhere too. Let me see if they give you properties of logs. Hey, what do you know? That's reference page 4, Laws of Logarithms, property number 2. Except they use an arbitrary log. They use log base A of x over y equals log base A of x minus log base A of y. That's the formula in your formula sheet. Is a natural log a log?
It's
Yes?
log of E.
It's log base E. So when you have log base E, that's the natural log. All right, so that would probably be the answer that would appear in the back of the book for that. All right, everybody happy? The way you feel right now.
No.
No, no, I'm defining happy to be the way you feel right now. That's happiness. That means you'll be elated later, right?
Yes, I will. I guess
All right, we ready to be done with this for now? I really have not come up with a good homework assignment for this because, you know, we've done so much integration now, and I told you to skip all the ones with the numbers. You know, so I mean, if you really want to practice this, I would say just go back and go through your homework. In each section, pick, you know, 2 or 3 problems that you've already done. Take that antiderivative that you had and try plugging in the numbers now at the end. And that would be how you could prepare for this a little bit. Does that make sense, what I'm suggesting?
Yes.
Okay. So we're going to move into the last section. We only have 20 minutes, but it's enough time for me to introduce you to it. And what are called improper integrals. These are integrals that just kind of, but they're improper. They don't behave well. They say the wrong thing at the wrong time. Socially awkward, kind of. Now, what's an improper integral? We actually have 2 types. Okay, so when we refer to what are called improper integrals, there's a type 1 and a type 2. We'll spend a little bit of today on type 1. We'll finish off type 1 next class. We'll get into type 2 next class. And then probably next Tuesday, we'll wrap it all up and then talk a little bit about the test, and then you'll have your test. This will be on it, though. I have placed all the videos for the homework assignment for this section. They're already up on YouTube. I finished the whole assignment today. So you have access to all the odd problem solutions worked out. All right, so we're going to talk about type 1. Okay, type 1 are called infinite intervals. So what we've seen so far, and it's not really like we spent a lot of time on this. We've only spent maybe a day on the concept of the antiderivative and the fundamental theorem of calculus somehow giving us the area underneath a curve between 2 points, right? Between A and B. What we're going to do now is we're not going to restrict ourselves to a finite interval. We're actually going to let the interval become infinite. So instead of saying, okay, stop at B, I'm going to say don't stop and find the area. And that may seem kind of weird because you may be saying, well, there's going to be an infinite area then, right? I mean, if you're going to keep this function going forever and never stop it, then ask me to get the area, then it's probably going to be an infinite number. But if the function behaves properly, then sometimes that area is finite. So let's look at this right here. It says anytime we have an integral where your limits of integration go from a and never stop, so to say that I go to infinity, or instead I go out to the left infinitely, which would mean negative infinity to, what do I use there, b? Yeah. b, or if your integrals have an infinity on both ends, then these three sorts of integrals are type 1 infinite intervals. So here's some pictures, just to show you a picture. This is an example of where you're trying to find the area here between 1 all the way out and you never stop. Now, does it appear to you that that function has an asymptote? Right? It's going towards the x-axis, getting smaller as you go. But it never actually gets there, does it? So does it make sense for me to actually talk about the area from 1 out forever? And is that number finite? Well, we'll have to figure that out. Sometimes it will be finite, sometimes it won't. Here's the other direction. You have a function, and you're stopping on the right side, you're actually stopping, but out the left side, you never stop. That would be this case. And then you could have a combination of both, which would be something like this, where you have a function that you go out both ends forever, right? Both ends forever, and you try and look at the area, and that would be this type. I'm sorry, they're all the same type, but that's what the integrals would look like. And these right here are of particular interest. These are used a lot in statistics. Anybody that's ever heard of a bell curve, right? Heard of the bell curve, standard normal bell curve? I think I may have mentioned this in the very beginning of class. But when you have a bell curve, it looks like that, doesn't it? If you take 1,000 men and you measure how tall they are, right? You're going to get some average, right? You're going to get like the average height. You're going to have a lot of men that lie in a certain window, and then they're either going to be really tall or really short. But as you move out to the sides, the number of men that are really tall goes down, right? And the number of men that are really short goes down. So both ends of the curve get smaller as you go out to the side. That's a standard normal bell curve. Well, in statistics and probability, what we want is a function that when you look at it and you take the area in both directions forever, okay, the area infinitely, you want that area to be 1. If you can find me a function that does that, where you go both directions forever and you get a total area underneath that function of 1, then you've created what's called a probability density function. And they're very valuable because if the area is 1, then I can look at the height of this right here as the probability that a person would, let's say, be this tall. That's the height. So however tall this function is. But when you talk about probabilities of events occurring, have you all heard from statistics that the total sum of all probabilities has to be 1? No? How many of you taken a stats class? Anyone here no one's taken a stats class? Oh, I should just shut up then. Nobody's taken a stats task where you flip to the back, stats class where you flip to the back of the book and you look at a table? No? Okay. Well, then you don't know what I'm talking about. I'm sorry. It doesn't help if you haven't seen it, but think about it. You know, if you have a standard 6-sided die, right? Right. If you have a die, you roll the die, right? There's so many different ways that this could happen. You could have a 1, you could have a 2, a 3, 4, and a 5, and a 6, right? What's the probability of each one happening? 1/6, right? 1/6. So if I measure this and say that's a rectangle, 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 that's a rectangle. And let's say the width of each of these rectangles is 1, right? Then the area of this rectangle is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. If you add all those up, you get what? 1. That's what a probability density function needs to do. The sum of all the probabilities has to add up to be 1. But see, the thing about rolling a die is that the values that can come out are finite. I mean, are discrete, what we call discrete. You can't get 1.5 when you roll a die, right? But not everything is discrete. When you measure people, it doesn't have to be exactly, you know, so many inches. You can have decimals, can't you? So you can have all the numbers in between. And if you include all the numbers in between, this no longer looks like a bunch of rectangles. It looks like a smooth, continuous curve. And then you want the area underneath to, again, add up to be 1. And that's where this whole thing with what we're doing here comes into play. So, all right. I think I've stretched out further than I can here. You just have to trust that these type 1 indefinite integrals, or infinite intervals, right, these improper things are very useful. Very, very useful. Okay, so how do we handle these? How do we handle these type 1 integrals? So I think what I'll do is I'll start with an example, and then I'll refer back to the notes. It's easier if I do it that way. So let's take a look at the integral from 1 to infinity of 1 over x squared dx. What I like to do when I'm doing these improper integrals is first just draw a number line and then put my what? I'm going from 1 to infinity, right? So I'm going 1 out this direction forever. Right? Then what I'm going to do after I draw my little kind of interval of where I'm going to be is I like to get an idea of whether or not this function has any discontinuities, whether or not the function has places where the function is undefined. Does this have a place where it's undefined? At 0, right? We have discontinuity at 0. Is 0 in here? Right? 0 is over here, right? I'm not looking over here. I'm looking over here somewhere. So I'm checking that, and the reason why you need to check it is because the type 2 improper integral is when this is 0, or when the bottom is discontinuous, or the function is discontinuous, and that lies in our interval. How do we handle that? So we look, there's our interval, the discontinuity out here at 0 I don't have to consider. All right, so here's the standard setup. What we're going to do is we're going to take a limit. Just write this down, we'll talk about it. If I don't put this limit here, right? If I don't put that limit right there, what does that represent? Geometrically, what is that? Geometrically, what does that represent? The area underneath that curve from 1 to t. And t would stop somewhere, right? So what I want to do is figure out what that turns out to be, and then let t go to infinity. That means let that thing go out. Let that t where I stopped, just let it go. And that'll take off to infinity. Does that make sense? So that's the idea. It's like we're stopping it at t to get an answer, and then we're letting t go out to infinity. All right. This equals. So you need the antiderivative of that, right? Right? You need the antiderivative of that. Also, the limit we have not taken, right? The limit is going to come in at the very end of the problem. We're going to actually take the limit. So the limit's got to come with us. And now you need the antiderivative of this. So what is it? Negative 1 over x. Is that what I heard? That is the antiderivative of this. Because that's really x to the negative 2, and then you add 1, and then 1 over that, and you get this. That's the antiderivative. I have to evaluate that antiderivative where? 1 and t. Okay, so let me kind of highlight things here. This piece right here turns into this piece right here because of the fundamental theorem of calculus, right? Like if that limit wasn't there, right? That red piece means this red piece, yes? Because of that. And what am I supposed to do with this? Plug in, right? Plug in the 2 points, and then the limit is still out front. So I get limit. T is going to go to infinity, but not yet. Of, I plug in t, then I plug in 1, I subtract the 2, right? So I'm going to set up my 2 sets of parentheses here again. But notice that those 2 sets of parentheses are living inside of the bigger parentheses because I still have to take a limit. What happens if I plug t in for x? -1 over t. That's it. What happens if I plug 1 in for x here? -1. And now, let t go to infinity. Right? We've done the plugging in. We have an expression. There's t. Let t go to infinity. What happens when you have a number like 1 and you divide it by a number that gets huge?
Starts going small.
Gets smaller, right? That gets smaller? So this piece goes to what? 0. See, no more limit because I'm actually letting t go to infinity. That goes to 0. This right here, there's no t in it, right? So there's just plus 1, which is 1. The answer is 1. So let's just discuss geometrically real quick what this is saying. If you were to graph 1 over x squared, so you get on your little graphing calculator and you graph it, 1 over x squared is the function. If I went out to 1, where would I be on that function? If I plug in 1, where would I be?
1.
Up at 1, right? Where would I be if I plug in 2? 1/4, right? If I plug in 3, I'd be at 1/9, right? And so as I go out, this thing is diving down towards 0, and it's going pretty fast, right? It never gets to 0. Never. So if I were to take this asymptotic function, and I were to look and try and compute the area under this thing forever, what I can tell you is that that area converges to 1. That means it gets very, 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 very close to 1. That does not mean it is 1, because if you ever stop, if you ever go out here to like, you go to 1,000 and you actually replace your t with 1,000, you will get a number and it will not be 1. It'll be really close to 1. If you go out to 1 billion, you plug 1 billion in here, you're going to get a really, really, well, the number is going to be really, really close to 1 again. Won't actually ever be there. If there was some way that you could go forever, then you would theoretically have an area of 1. Does that make sense? That's why we use this term converges to 1. So what we're going to see next class is that if we do this limit and we get something that's not finite, like let's just say that this, instead of this, was t, and I let t go to infinity, this piece would become what? Infinite. And then what we would say is that the whole area blows up. And so this integral, the answer would not be infinity. The answer would be, instead of converges, we would say the integral diverges. So that's what we really are trying to get to with these improper integrals. Does the integral converge? If so, what number does it converge to? Or does the integral diverge? Can we start a sign-in sheet? Or wait, everyone took the quiz? Everyone took the quiz, right? No one skipped it? Okay, I'll take it off of that. I want you to think about this. You can start packing up.
Say after you hear it starts.
But I wanted to see what you thought of this. What do you think that's going to do? Think it'll be 0? What does cosine look like? Like this? What do y'all think? How many think 0? Anyone think anything other than 0?
If you define it, you have domain restrictions, it should be.
So look, I said you can pack up, but please give me your attention, okay? If you were to actually just go out to 2 pi, we showed that the area right there would be 0, wouldn't it? But if I stopped a little bit past 2 pi, would it be 0 anymore?
No.
Okay, if I stopped like right there, would it be 0 anymore?
No.
It's only going to be 0 at multiples of 2 pi, isn't it?
Yeah. See, that's
So if you're going to infinity, how can you say it's 0? Because as you move on, like yes, you will, if you think about like accumulating the area, like right here I have some area, right? Positive area, and then it's probably still positive, and then at some point it counters it and it becomes 0, doesn't it? And then it's like positive, a little negative, now 0, then positive. And so as you move on, the area behind you is changing, isn't it? As you move across, the area is actually fluctuating. In the last problem, this, as I went out, the area behind me just kept getting smaller and smaller and smaller, right? I mean, as I moved out, every single time behind me the function was collapsing down to 0. This function's not collapsing behind me. It keeps oscillating back and forth. So do you think it converges? Do you think it actually goes to a number then, the area? Yes or no? Do you think it goes to a number? Probably not. Probably not. So in the case that it does not, we say it diverges. So this is actually this would actually diverge.
for every multiple of 2 pi, the converges to 0.
Well, no, because convergence requires that we don't just pick certain places. You could say that integral, right, this integral, let's call it k, is equal to 0 whenever k is this. But if you change it to infinity, it's either going to converge or diverge. It's one or the other. Okay, homework. What's your homework? I'm not sure we're ready to start anything on this. Let me tell you what it's going to be so you can at least have this. It's going to be 6-6. It's going to be off of page 360. It's going to be 5 through 31 odds. And you could do number 5 and number 6, even though I didn't assign 6. You could do number 5 and 6 and 8 and 9 right now if you want to try and get ahead. 5, 6, 8, 9. If not, get caught up. I know a lot of you said you still weren't done with the partial fraction homework. Get that done. See you on Thursday. Yes? Improper integrals will be on the exam.
Sir, I have a question.
Okay, let me turn my recording off.
Sure.